Okay, well, we're back. Normally, you guys can't see this, but Charles is just on the other side of this. He's there, so I have someone to talk to, because talking to the camera is too weird. So we're back. What was the line you used last time? They didn't go anywhere, or you didn't go anywhere, but... No. Anyway, so we're going to be talking today a little bit further about monadic design patterns for the web. And just to kind of remind everyone what we were doing last time and the whole scope of this stuff. I'm really interested in how monadic techniques allow us to structure applications that span, from the browser to the back end and back. And before we can talk about, sort of how we can use them to manage the domain model or the storage model or manage the request stream, we were introducing some tools. And so I'm gonna kind of finish off the toolbox with a lot of suggestions about how they begin to apply in these different areas. So previously on monadic design patterns for the web, we were talking about monads as funny, fuzzy, warm things, which is a joke from the Haskell community, and really the thought was that monads can be seen as shapely, in the sense that they're the three key ingredients: shape, wrap, and roll. And the idea was that we can build one canonical mental model, which is this idea of colored braces. So shape is the color of the braces, wrap is putting things in between braces, and roll is flattening up nested braces. That's the basic idea, and we encapsulated that, say, with some XML representation of set. This is just syntax for how we might write down set. And so shape is, again, just putting things between the color of the braces, wrap is putting things between braces, and then roll is flattening out these nested braces, just like that. Now, even there, and this is where I get totally excited, because it's always these little gotchas, these little details that I love that open up these whole other worlds. And that's what literally, when I started thinking about monads, that's what happened for me. So the thing that I noticed immediately was there are really two kinds of collections. And if you're a programmer, you know this in your bones, but maybe you don't say it so often. But there's the words that are used in the theoretical literature is extensional and intentional. And what do we mean by that? Well, an extensional collection is something that we can write down. We can give each element of the collection. Whereas an intentional collection, we have to somehow specify programmatically, such as by a rule. So let's give some examples of that. So these are kind of, standard programming 101 examples. You have the set that contains A, B, and C, or the list that contains 1, 2, and 3. And I include this one because you might think this is not really a collection, but that's where monads kind of blur the line a little bit. If we think of this syntactically, right? I've got the syntax of a sum that adds up the result of taking F on 1 and G on 2 and H on 3. So syntactically, this is still a collection. And now let's, and this is kind of an important example, and I've kind of set these up to line up this way. So when we want to talk about infinite sets, which are very important in programming. For example, we might pick out the even numbers, so that all the A's in the natural numbers, where if they're evenly divided by 2. That's an infinite set, right? And there's another common infinite set, is sort of, again, programming 101, and that is the Fibonacci's. And this is sort of a trick that we can use in, say, Haskell or Scala to calculate the Fibonacci's, where we recursively zip up the Fibonacci's with itself using the addition. So we just kind of shift it over and add it to itself. That's what's going on here. But again, the point is, for this, it's not so important that you understand the programming syntax, but just that here I've recursively defined the Fibonacci's. So I have a little program or a rule which picks out this infinite set, and that's quite different from the, this infinite list, which is quite different from this this finitary list. And there's a neat point to notice, right? Which is that even though this is infinite, in some sense it's very much akin to this example. Why? Because we still write down a finite number of characters to express it. And that's somehow important, that as programmers we have magic available to us. And what is that magic? That magic is that somehow with finite means we can access the infinite. We can manipulate the infinite. And that's amazing. And there also, you know, this is just high school mathematics. We note that there's this transition point, even in ordinary high school mathematics, where we start to notice that, hey, there's some sums that I can't write down in a finitary way. And that's where this sigma notation comes. That's why it's introduced when we start talking about series in high school, right? It's like if we take the sum of all the powers of 1/2, right? That's an infinite series, and we want to reason about those infinite series, and there are all kinds of reasons why we want to reason about that, but we can't write it down unless we invent some kind of notation like that, right? Now really what's going on monadically is that underneath the covers there's a fold going on here, which we'll get to a little bit later. But again, the big picture is extensional versus intentional. And that opens up all kinds of fascinating worlds. But let me hit some reasons why you want to open up to the intentional world. And that is because, first of all, it's not just these cutesy mathematical examples that are infinite collections, right? Languages, so all the utterances in a programming language, right? All the sentences that might be generated by, all the XML documents that might be generated from an XSD schema, that set is somehow infinitary, right? So those are some pragmatic infinite collections. Another example, and this is fascinating because the point is not just about being infinite, where we might take up all the memory resources in a computer. It's also about taking up compute cycles. We might have a finitary set, but computing each element in that set might take a long time, right? So we might have some linear programming problem, or we might be running the simplex algorithm, and computing which elements of our constraints actually satisfy all the constraints might take a very long time. And so if we can somehow express that programmatically and defer those computations until just when they're needed, then we can kind of conserve our resources, in particular the resources being compute cycles versus, say, memory cycles. And then finally, you know, once you go down that once you start down that slippery slope, well, there's another avenue that opens up, and that's collections that are calculated from the environment. So I might actually, you know, have context-based menus, right? I'll actually compute a menu on a UI on the basis of what I know about the history of the user actions, and that's commonplace today, right? But I can't do that from the outset. Like if I tried to list out all of the options of a menu, that would be a very tedious way to construct menus. I have to programmatically construct menus, and that requires input from the user. So those are three common cases where we need intentional versus extensional collections. So then again, just the point is we want to be lazy about intentional collections in many cases. When we're dealing with infinite collections, so the size of the collection is unbounded, then we need some kind of just-in-timeness in order to avoid consuming all the memory available on the machine, or machines, if we're running this on a farm. Likewise, if we're using the algorithmic aspect of the specification of the collection to give us some kind of compression, then we can use laziness or just-in-timeness to avoid unnecessary use of cycles. And then as soon as we make this jump here, that blurs the boundary between computing something just in time and I/O. Like, how do you know, if I say, well, I'm going to hand you whatever you're asking for, you just got to tell me a little bit about what you need. Now, how do you know whether I'm computing it or on the basis of your description I'm going off to a store and fetching it and bringing it back? Right? If I do sort of encapsulation, sort of typical computer science object style encapsulation, you can't really know that, right? You stand on the other side of that interface or API, and so that boundary becomes blurred. So those are the three aspects that come out of these situations. And again, I don't want to be abstract about this, right? One of the things that the Web 2.0 has taught us is that seemingly small, simple things like a data type of 140 characters gets really interesting and valuable when it's iterated into a stream. So somehow this iteration process, this infinitary collection thing, is very interesting, right? So we need a syntax, and it turns out, and I've talked to so many people so many times about this. I forget whether in this context we've explored this, but it turns out that what is called comprehension notation in set theory, which later got adopted by many languages, from Python to Haskell, is completely isomorphic to the for syntax, say you find in Scala or other languages, and that's also completely isomorphic to the select from where syntax. So these are actually 4 or 3 different ways of saying the same thing. Okay, and spelling out the isomorphisms from this form to this form to this form is actually quite interesting. But it's also really interesting to note that somehow this for notation seems so imperative, and this select notation seems so declarative. and this also seems very, very declarative, and yet somehow they're all pointing at the same underlying phenomena. And we have to have a notation like this because, like in the case of sets, right, we either list them all out or we say, give me some pattern where I'm filling in elements of the pattern from these sources only in the case that they satisfy those conditions. Right, so that syntax is a necessity, or some variant of that syntax is a necessity if we want to be able to handle these infinitary collections. Okay, so already we've spotted this little opening. So the opening was, we have this notion of shape, wrap, and roll. What can go in the braces? Well, if I'm limited to just writing down, ploddingly, one after a time, what can go into the brace, I'm kind of stuck, right? And that's this one. And to unstick myself, I have to invent some other kind of language, which allows me to specify them programmatically. But it opens another question, and that question is, hey, I kind of understand what generator syntax might be like, because this is really coming directly from the constructors of the type we supply for the collection, right? So if A tells me how to make A's, then I can kind of understand what sort of syntax I might have for generators. But what syntax do I have for writing down conditions or patterns, right? Now, the average programmer say, well, it just comes from the ambient language. You embed your notion of comprehension in Scala, and you've got Scala. You embed it in C#, you've got C# syntax, or F#, etc., right? But there's an interesting point, which is there any way in which these things, this pattern language and this condition language, can somehow be tied back directly to the original type over which we do our collections. So that's an interesting question. And here's another interesting question. And this is a what was that about hats kind of thought. Now, why do I mention that? Well, I'll show you in a minute. But the real interesting thought, the thing that ought to make people twig, is if you think really hard about shape, wrap, and roll, what's inside that API that allows me to get anything out of the container? Right? Wrap, well, shape just says what the container is, what its shape is. Wrap says how to put stuff in, yep. And roll says how to flatten nested ones, but you always still end up with a box. How do I, once I put stuff into the box, how do I get it out? Okay, so now we have three kind of openings into this other world. So along those lines and along the lines of the, oops, I don't want to go there just yet. Here's a kind of a slight digression that sort of frames this. Let's see if I can grab it. Hang on. So oftentimes we get pretty distracted, and we don't go back and follow up these little questions. Okay, so there are these big opportunities in these tiny little questions. And in particular, what comes out of this question is that monads are not enough. Really, there's a kind of $64,000 question. I guess that's from a different economy, different economic times. No, but there's a big question behind this one, which is that if monads are sort of the new object technology, monads are the new way to structure code in a composable way, well then how do we compose monads? Right? And it really, really is important to show that they do compose. And what we'll see if we take this question on, and I hope that we do in this series, is that monads are not quite enough. You have to have a way to get stuff out. And the way to get stuff out is what's called a comonad. Okay? And most data structures, I'll just say this up front, I'll give the punchline first. Most data structures that we deal with on a regular basis, sets, lists, whatever, they're actually pairs of monads and comonads. A way to get stuff in, a way to get stuff out. Okay? And it turns out that we can kind of structure the flavor of the stuff that's sitting underneath a monad. Sometimes I call them three different flavors of monads, but it's really, there's something underneath the monad that the monad is an API for. And you need to widen the API to include this other capability. And then we start to see the thing that we're really manipulating. So, let's go and look at that. So again, I hope you've noticed the sleight of hand, because I opened up this other question here, which was, where does the language for patterns and conditions come from? And now I've distracted you off onto this other tangent. And I've done that on purpose. So now people actually get confused. I know I was confused by this because there's an interesting capability even within the monadic interface. So when can you check an element out of a monad? Well, you can check out anything anytime you want using map, but you can't ever leave. So monads are really like Hotel California. And to kind of get this here's a little bit of Scala code. We could have written F# code or whatever. I use Scala because whatever. It's nice and compact and neutral. Okay, so suppose that I've got a oh my goodness, this should have been normalized results. There's a typo here. I'll just quickly fix that.
Great.
Go back. Okay, so suppose a we're doing an analytics application. We're doing some kind of financials application, all right? And we can go and get raw financial data from the web, okay? So we get some raw results. And just like with other data that's out there, either in a store or available via web service, sometimes there isn't anything there. So we wrap it up in an option, okay? So options are a form of monad that people may or may not have seen. I didn't introduce it, but it's a common monad. You have basically two branches. Either you have nothing or you have something, okay? And you wrap up the sum in some kind of constructor like something, and then that allows you, with pattern matching, to pull it out. So we can get our raw results, and we either get nothing or we get something. Now, the interesting point about the for construct, which is isomorphic to the set comprehension or the select from where, is that we can go and pull the result out of the intermediate results. So if there was something there, result will be bound to the thing, and then we'll yield the normalization process on the result, but it will be packaged back up in the option. So we'll only run this in the case there's actually something there, but we don't get something back out. We'll get option something, right? So normalized results will take something that is of type A. So result will be of type A. So we're peeking inside the box. We're running something on the A's, getting a B, but then we don't actually get to get out of the box. We wrap it back up in the option. Okay, so that's what this looks like in something like pragmatic code. Now, if we unpack this in a generic way, what's really happening underneath this for notation, if I just consider one generator and one condition and one yield, what really happens is I run a map. Remember, we talked last time about the notion of map, which allows me to take any old function and run it pointwise over all of the elements in the collection. Okay, so that's what's happening here. I have some function which takes a p, and then we pattern match that p against two possible cases. One is the pattern that we have here, and then we check our condition, that's this, and we run our expression on the pattern. That's in the case that we got the match. In the case that it doesn't match, we throw some exception. This is effectively the semantics. So now we can see exactly, this lines up precisely with the type construct from before. Map takes a function from A to B and turns it into a function from MA to MB. That's what's going on here. We never get out of the monad. Oops, wrong direction. Okay. So the question is, are there three kinds of monads? Well, we can think about the I/O monad. This is, I'm pulling stuff off of some input stream. Okay? And this one is the classic, and this is the one that trips people up when they first look at monads in Haskell. Because they start writing code and then they realize, oh man, I can never get the data out of the I/O monad. So that's really, stuff goes in but never comes out. Okay, and then there's stuff goes in and sometimes comes out. Right? And this is nearly all the standard collections, right? So if I have a list and I put something into it, I fully expect to be able to get that thing back out without it being all wrapped up in listness. Sure. Right? The listness disappears somehow. Okay? And then there's one that is only, it's a kind of it's a kind of data structure that people are only starting to really wrap their minds around. But whereas in network protocols or other kinds of disciplines, sometimes storage disciplines, this idea has been around for quite some time. But that's the idea of perfectly matched into and out of. Right? So every time I put something in, there's got to be a corresponding take something out. Okay, now if you think about it, right, this is not unfamiliar. HTTP, I make my request, and I don't go forward until I get my response. A request-response protocol. What HTTP doesn't have, that this idea does have, is the idea of nesting that idea. Okay, so let's talk about that for a minute. I can make a request, and now I'm kind of in the middle of the state. It doesn't allow me to make another request, and make another request, and then when I get the response to that, I pop up. But that's just, all that is nesting parens, right? Nesting balance parens, right? Request is the open paren, response is the closed paren, right? A perfectly valid structure is just any nice little S expression with the balanced parens, right? And we could imagine that we could have an HTTP-like protocol that was fully request-response, but had this balanced parens type shape. What would that correspond to? Well, that would correspond to exactly the idea of session state. And that's where, like recently, people have been looking at session types as a way to ensure session-like behavior in session state in protocols that are slightly richer than, say, HTTP. Because right now, what do you have to do? Well, HTTP is one of these just stupid enough protocols that you have to introduce things like cookies and other state mishigash. But that creates a bridge to something that is very important, and that is that each of these corresponds to a transactional mode. Okay, so why am I talking about this in this context? Precisely because I promised a bridge between monad as container and monad as control. And we're beginning to build that bridge. So what we're starting to see is that somehow there's a relationship between container and control. Each of these ideas corresponds directly to a transactional mode. Now, what do I mean by that? Well, the stuff goes in and never comes out idea is exactly the messaging-based transactions. I fire off the message, I press the button, and the missile launches. I can't get it back, right? I'm not pulling that one back, right? Now people think about a variant of that where they have a poison pill. Okay, so I fire off the message, and if I'm lucky, I can send a cancellation message. Oh yeah, I want to take $50 out of my account. Oh wait, no, let's not do that. Okay, so we'll just recredit the account with $50. Okay, and that corresponds precisely to the stuff goes in, and sometimes comes out, right? So there are certain conditions when it goes too far. Oh no, I'm sorry, we already paid that. I mean, you can't get that money back. You know, sorry, we don't have a return policy on that. That you can't get this stuff out of the collection. And then there are situations, there are transactional modes. So for example, in an ACID-based system, you do have a rollback for every action until the commit. Okay, so that's how these ideas correspond precisely to transactional modes. Okay, and it turns out that the monadic machinery constructs this nice API which gives you a uniform way of dealing with collections, control, and these transactional modes. Now so I want to make a nonlinear jump here. That should begin to suggest why this structuring technique is so important. Because we have just now touched on dealing with I/O streams, dealing with our domain model, and the transactional nature, being able to specify some variant of a transactional nature for requests that touch state all the way in the back end and go back. All right? That should begin to get our viewers. Hi there. Mom, are you out there? Get our viewers interested in this as a structuring technique for these kinds of applications. I just love that burn. All right, so it turns out that the three kinds of monad actually have connections to logic and connections to control. I think for this session, what's the time like on this now? Oh, we're coming up on time here. So I'm gonna skip the connection to logic and defer that to next time, and go right to the connection to control, and then in the next section we'll talk about the co-connection, which is wedding the monad and the comonad together. So we might imagine a key value database, right? This is very common these days on the web. But we might implement the key value database in a really interesting way. So so associated with keys, we have both locations and another little, so this is, you could think of this as a one-place cell where we can store one thing exactly, okay? But then we also have another kind of store which stores the continuation of a request. So what do I mean by a continuation? Well, I've kind of tried to indicate that down here this way. So we imagine that these are sort of computations with each step going off in time. So first we do this step, and then next we do that step, then next we do that step. And if there were branching structure, you'd see sort of branching streams of these icon figures going off into the distance. So in the case that, say, this computation and this computation head off to this key to go get some value that should be deposited there. If there's nothing there, then we can imagine that our key value database grabs the continuation of these computations and stuffs the continuation up into the store, okay? So then, if another computation comes along and says, you know what, I'm going to deposit a value at this key, then the semantics, I guess this really doesn't show up. Hopefully on the direct feed this will show up. But so there's a value sitting here, a little black hole. The value would normally be deposited here, but because we have an awaiting request, we pop off the awaiting request. And the value, so there was a continuation, which was the guy in front here, right? The continuation now gets popped off, and this guy, you can't see it here, but on my screen there's a little value that is now accessible to this point in the computation. Now, if this computation in its next step deposits another value at the key, we still have an awaiting computation. So what will happen is the value, that continuation will be popped off, made available to this computation at this point. And now, if the computation over here continues again and deposits yet another value, there's no awaiting continuations, and so the value gets deposited at the key. And then if another computation were to go and request it, they would immediately get it back. Okay, so this is a kind of rough and ready way to think about continuation-based key value pair database. All right, and you know, guess what? This is used on a regular basis in web servers today. Okay, but now here's something that is eye-opening in terms of the way we might think about the relationship between control and container. If you think about a tree, you think about a list or a graph. Each location. Let's take a list. List is the simplest example. Each location in that list could be thought of as independent, right? We could just explode all of the locations. Another way of saying this is, and this goes back directly to the little jam session that Brian and I did, right? And this was his insight, that somehow the list structure gives me a way of addressing content. Okay, that should be very, very suggestive. When we're buildings, one of the primary functions of the built environment is to address people. Okay, so that's exactly what monads as collections are doing. They're addressing content. Now, we don't have to have it be that there's any sort of physical correlation between the locations, between or amongst the locations in the structure, right? We might have a metaphor in our minds that there's some kind of tree structure or some kind of nesting physical structure, but that's not a requirement, right? We could take each of the addresses in the list and explode them, just flatten it all out. Now, what does it look like? Well, it looks a lot like a key value database, okay? So in other words, each of these keys, if we did things just so, could correspond to a location in the list. And then the important point would be we would have to arrange it so that if I got a value here, say popping off the head of the list, then any computation moving forward that saw that state would have to know that we have, you know, the tail of the list. So there would have to be some relationship between, for example, if I have locations and values stored here, I'd have to know to pick it up. If this was the beginning of the tail of the list, I'd have to know to go to this location to forward further requests. So that begins to suggest what's happening here. So, and in point of fact, the transformation of a collection like this into this flat structure is very much like what happens when compiling collections down to machine level anyway. Right? So that's a nice little scale invariant image, right? That's a fractal-like image. When we start thinking about going either below the sort of programming model level down to the machine, or above the programming model level to, say, some storage in the cloud, we might go through this transformation step where we flatten out these locations. Okay, so actually, what time is it? The next phase starts to get more technically complex. So I think what I might do is stop there, because otherwise we'll end up getting really, you know, we'll be cut off in the middle of the technical discussion. Okay. Does that seem like, yeah, okay, great. So that's where we're going to stop for today, and then we'll pick it up in the next section to look at that transformation between the key value database and these collections, and how that relates the continuation monad to the collection monad. All right, so then we get this nice mediated structure, and then we can toss in our zipper. Cool. Yeah, so that's where we'll leave it for today.